is A-Level Computer Science 9618 paper 3. This is chapter 4 and this is part 2, system software. The topic is system software, and today we're going to understand about memory management. And inside the memory management, we will discuss about virtual memory, paging, segmentation, disk thrashing, the difference between paging and segmentation, and how paging is used for virtual memory. Okay, so let's start with paging. So memory management will determine which process should be in main memory. We are actually managing the process, and yeah, and we need to make sure that which process come into the main memory and where they should be stored. When a process starts, it is allocated memory. When it is completed, the OS deallocates memory space. Okay, it's common sense. It allocates memory, and when it's complete, it deallocates. The storage of process in main memory can get fragmented. That is the main problem. Fragmentation is a real problem, and it's the only reason why we are doing paging and segmentation. And virtual memory can eliminate both types of fragmentation, external and internal. Yeah, so fragmentation are consists of two types: external and internal. External fragmentation is when you are giving variable space, to each process. And if you are giving variable space to each process, I mean big and small, then there are some gaps left for, and if you just add all of these remaining gaps, it could make enough memory for one process to run, but that process cannot be fit into this because they are distributed. These gaps are distributed, so that's what we call external fragmentation. Total memory space is enough to satisfy a request or to result a process in it, but it is not contiguous, so it cannot be used, which means all space are not in one side, they are distributed. Okay, internal fragmentation is when we are giving equal space size, but it's more than what's actually required. For example, you need at least 80 kb, but you are giving 100 kb, so there's 20 kb free, there's 10 kb free. So these space are what we call internal fragmentation. Okay, so these space are left unused, they are wasted at some point. Memory block assigned to process is bigger, some portion of memory is left unused, so it cannot be used by another process. Okay, so that's the definition of external and internal fragmentation, and we need to decide whether we want to eliminate external fragmentation or internal fragmentation. Okay, paging, why do we use paging? Okay, paging leads to internal fragmentation, but it can eliminate external fragmentation. Okay, the important thing is it does lead to internal fragmentation. That's the only problem, otherwise it's amazing thing. Memory is split up into partition block of fixed size. That's the most important quality of paging. It's make a partition of fixed size, equal size. The partition are not necessarily contiguous. The physical and logical memory are divided up into the same fixed size memory blocks. Okay, the number of blocks are known as frame for physical memory, and number of blocks known as pages for logical memory. We know the difference between physical and logical, right? Physical memory is something which is actually there. Physical. Logical is when you are making a memory logically that should be applied. A program is allocated a number of pages. A program is allocated number of pages that is usually just larger than what is actually needed. Number of pages, which means number of this logical memory. We are giving number of pages, number of memories, 100 kb, 100 kbs, like that, but it is more than what is actually required. Okay, when a process is executed, process pages from logical memory are loaded into frame in physical memory. Okay, so pages are loaded into frames when the process is executed. Only some of the pages of the okay, this point here is telling the advantage of paging. Only some of the pages of the program are loaded to start the execution of the program. Programs process only some of the page of the program, which means so it's a whole program and we are only taking some of the pages, which means not the whole program is not being executed. Some of its services are being used. Okay, so that's the advantage of paging. Only some of the pages of the program and are loaded to start the execution of the program, which is in this way it saves memory. More program can be run, which means simultaneously so many programs can be run, and each program is giving some of the pages which are currently being used. Okay, not all of them are used. Each process has its own separate page table that maps logical address to physical address. So we need the page table in order to load from logical memory to physical memory. Okay, it contains the page number, flag status, page frame address, time of entry. Process of paging is essentially invisible to the user. It is invisible, it is not seen by the programmer or user itself. Page replacement occurs when a requested page is not in memory. Okay, it is not in memory. When we are requesting a page but it doesn't, but it's not, but it hasn't come into the main memory. So how to make a replacement of that, of the page which has been requested, that I mean we need the request page, so we need to make an arrangement for it. So there are two algorithms. The first is a page may be replaced simply because it arrived earlier than another page. Okay, it arrived earlier than another page. FIFO, first in first out. A page may be replaced simply because it arrived earlier than another page. So we are determining which page should be replaced. Okay, that's what's happening. LRU algorithm is the page which has not been used for the longest time is the one would be replaced. Maintains a linked list of all the page in memory with the most recently used page at the front and the least recently used page at the rear. Okay, so the least page, so the page which has been used very not often, not at all, will be replaced. Okay, will be replaced by page which we need in the memory. Now we will come to the virtual memory. Virtual memory is something that virtual memory is something which is virtual, and it helps you in a situation where a RAM main memory gets full and you need more space for the process to run. So you take some space from the secondary memory, which is your hard disk drive, which is your HDD. Okay, so it needs to prepare for a situation in which process run out of RAM main memory. So it can be solved by mapping each program memory space to RAM and utilizing the hard disk drive if we need more memory. Like I said, if the RAM gets full, it needs more memory. It will take some memory from the secondary storage, which means the hard disk drive. Okay, virtual memory is equal to RAM plus swap space on hard disk. It is implemented using demand paging. To execute a program, pages are loaded into the memory from HDD. Pages are loaded into memory from the HDD, from the hard disk drive. Okay, it gives the illusion of unlimited memory being available. It eliminates external and reduces internal fragmentation. Okay, disk thrashing. What is disk thrashing? It also related to virtual memory. As main memory fills, more and more data page need to be swapped in and out of virtual memory. Swapped in, out, swapped in, out. Okay, this lead to high rate of hard disk. For example, you have the RAM, you have the hard disk. It goes in, comes out, goes in, comes out. Swap in, swap out, swap in, swap. It goes so fast. Then it leads to a high rate of hard disk read-write head movement, and this could make a lot of problem. If more time is spent on moving page in and out of memory than actually doing any processing, then the processing speed of the computer will be reduced. This definition is known as disk thrashing. Okay, more and more data need to be, more and more page need to be swapped in and out of virtual memory. This lead to high rate of hard disk read head movement, which means it's known as disk thrashing. Okay, this definition is known as disk thrashing, and this is the point of disk thrashing. A point a point can be reached when the execution of a process comes to a halt since the system is so busy paging in and out of memory. A point can be reached when the execution process come to a halt. You got the example. Let me give you an example. This might be the example when obviously I have experienced in my own mobile phone, in my own Android phone, when my space, when for example I have 2 GB RAM mobile and I'm playing video games. So when the RAM gets full, it takes some memory from the hard disk drive, so it gets slower and slower. And this would be possible in a situation where you are playing video games, you are listening to music, you're putting so much effort, so much effort on a RAM that it gets full, and you're doing so many things that it comes to a point when that it gets hanged completely. It gets to a halt. This is known as thrash point. Okay, thrashing can be reduced by installing more RAM space. Okay, segmentation leads to external fragmentation. Paging leads to internal fragmentation. That's the difference. Logical address space is broken up into variable size. In paging it was more like equal size, but in here it is variable size. Memory block position partition called segments. Segments from logical memory are loaded into physical memory. We use it in we use this for segment map table is used just like in paging table. The segment map table also used very similarly, contains the offset value, the segment number just like the paging number, and start address in physical memory. Okay, if you combine these two, it will form the address of a segment in physical memory. All right. Okay, the segment in logical memory do not need to be contiguous, but once loaded into physical memory, each segment will become a contiguous block of memory. So that's a different. The paging doesn't in the paging it doesn't need it's not necessarily to be contiguous, but in here each segment will become a contiguous block of memory. Okay, it becomes contiguous. Segmentation is essentially a visible process to use a program. It is very visible. So that's a different. Paging it was invisible, but here it is visible to the programmer. Okay, so that was segmentation, paging, virtual memory, and that's the end of memory management. Now we are coming to the next subtopic, which is translation software. Contains 4 stages. Okay, the one is the stage of compilation of program. It contains 4 stages: lexical analysis, syntax analysis, code generation, optimization. So first of all, let's start with interpreter. We already discussed this in P1 computer science, so I'm not going to go into much detail about this. We all know the difference between compiler and interpreter. Compile the whole thing in one go, and the source code gets hidden, while the interpreter it just interpret one line at a time, and it's very useful for debugging. Okay, but it doesn't compile in one go, and so since it's interpreting one line at a time, it needs object code. I mean, it needs the source code every time. Okay, so as there is no object code produced from the interpreter will need to be used every time the program is executed, which means it needs the source code every time it is executed, which means the source code is always open whenever you use interpreter. That's a disadvantage, that's a security breach for you. Okay, that's why it's very you need to think wisely. That's why it's a big disadvantage, but if you want to use for debugging stuff, but interpreter is very useful. Okay, stages of compilation of a program: lexical analysis. Unnecessary characters not required by the compiler, such as white space or comments, are removed. Before translation, the source program need to be converted to tokens. Yeah, the tokens, the source program need to be converted into tokens, having like keywords and all the having keywords, they are the whole thing converted into token. This process is known as tokenization. You have a token table. Okay, in order to tokenize the program, the compiler will use a keyword table which having list of tokens for each keywords. Okay, that contain all the token for the reserved words and symbol used in a programming language. Symbols and reserved words, keywords, okay, in a programming language. This happens in lexical analysis. Two things: removing any unnecessary things like white space, comment are removed, and the second thing is when you are doing tokenization, making a keyword table having list of tokens for reserved words. Okay, that's lexical analysis. Syntax analysis, when it is checked for grammatical syntax errors. Okay, it complete to it is complete to canonize sorry it complete tokenized list is checked for errors. Complete tokenized list is checked for errors using the grammatical rules for the programming language is called parsing. The rule for parsing can be set out in BNF notation, backslash no nor form. We will discuss this later, it comes later. Then in the third section, in the third stage, it comes code generation. It produces an object program to perform the task defined in the source code. The object program is in machine readable form, and when it is machine readable form, it executes much faster. Okay, that's the advantage. Optimization, when you are optimizing, you're making it more efficient. You're making more efficient. For example, you got the original code, it's separated, and but you can see it is this thing is the same as this, but it is in different line, so there's repetition. So when it is optimized, then you can use the same variable in here. So it means the same thing. Okay, w is equal to x plus y. Here is x plus y plus z. Same thing. You're optimizing. You're making it much better, making it more efficient. Supports the creation of an efficient object program. Okay. Then we come to expressing the grammar of a language. How the grammar of a language is created. We can create the grammar of a language using syntax diagram and BNF notation. In the syntax diagram, we try to show it like that the operator can have plus, minus, multiplication or division, or a variable can have a letter and it can have digits, and it can, you know, it can, like, I'm having letters again, I can have another letter, another letter, having a digit, another letter, and then woo, going there. So this is how you make a diagram. Okay. Then next thing is BNF notation, is when you use a set of symbols to describe the grammar rules in the programming language. And it can be used, grammar rules in a programming language can be used for recursive definitions. So what does it mean by the recursively? Recursive mean when you're recursive. What is the meaning of recursive? Recursive mean, for example, you have a function, and let's say function sum, and it's signed inside of this function sum. You are calling this again function sum, and then this function, inside a function you're calling the same function, so it keeps on going recursively. Okay, that's the meaning of recursive. We will understand this in P4 hopefully. So this is the example. Variable such as, this is mean such as or equal to, having letters, or this is mean or digits, having letter or digits. Letter is such as A or B or C. Digits is such as 1 or 2 or 3. Variable is such as a letter or variable letter. And this is the example of recursion. This is the example of recursion, because you are calling itself. So variable is equal to letter or variable letter, which means variable, if you choose, then variable consists of more letter, or variable letter. If you choose this again, then again it comes letter, variable letter. So it keeps on going like that. But if you want to solve this, then you can just choose this one, letter, and that's the end. So what have you chosen? You have chosen variable, okay, letter. You have chosen letter, then again variable, letter, then letter, which means you have chosen 3 letters, 1, 2, 3. That's how you make the grammar. That's how you make a grammar rules, okay, for programming languages. This is BNF notation package node form. Now we are coming to reverse Polish notation, and okay, so this is the end. Reverse Polish notation is something, it would be very tricky. Now there are three things I want you to understand before going to this. Infix, postfix, prefix. Infix is A plus B. Postfix is A B plus, and prefix is when you, now prefix is very difficult to tell you, but prefix is prefix, postfix, quite must be like PA plus AB, something like that. Okay, so when we talk about reverse Polish notation, we are choosing postfix. We are doing postfix. Okay, it uses postfix notation. It can be converted using binary, or it can be converted using stack, by to any one of these. But I would recommend using stack first and then using binary tree, because stack is very simple, very easy. I will tell you. So for reverse Polish notation is representing an arithmetic or logical expression without the use of brackets or special punctuation. We are doing graphically. Okay, let's start from stack. For example, you have this question, and you need to convert this is infix, and you need to convert this into postfix. So infix to postfix, how to do this? Okay, when you are doing with stack, there are so many rules I need to remember. The stack, the stack is looks like this, right? Stack and queue we have discussed it in paper 1, I think, in computer science P1. So whenever you got the letters, the letter will be pushed into the stack. Like for example, first of all you got the bracket. The bracket is put to the stack. Okay, there you go. Now you coming to the letter. The letter is print out. So this is the print. So used for operators, used for operators only, not operand. Operand will be print out, while the operand will come here and will be decided at which should be printed. Okay, operators and brackets. So first bracket comes and A will be print out, plus will come in here, B will print out, bracket, the closing bracket comes here. Okay, every time the bracket get closed, the remaining operators between these brackets will be print out. So for example, plus is in the between the brackets, so it will be print out. So plus is written here. Okay, now we are coming in here, multiplication comes in here, brackets come in here, C is print out, minus comes in here, D is print out, and the remaining bracket. Okay, now this one is closed, so minus will pop out, minus, and then remaining multiplication will come. There you go. This is postfix. This is complete postfix. This is how you do it. So this is how you do postfix conversion. But I didn't tell you about precedence, so let me use another example. Supposing I have this example, okay, I have using only 2 examples or 3 examples. Okay, 2 is enough. Supposing I have this example, okay, now I'm making a stack. This is my stack, and I need to convert this in postfix notation. I got the bracket, it comes in here. I got x, so I'm going to print this x. Now I got the multiplication, it comes in here. I got 2, so 2 will be print 2. I got plus. Okay, here's the thing. Now we need to understand about precedence. Precedence means giving more priorities to the operators. So precedence for the operators is minus and plus will be given the precedence of 1. Multiplication and division will be given the precedence 2. Okay, so number 2, number 1. So multiplication and division given the most priority, then addition and subtraction. Okay, now the rule is whenever whenever a smaller precedence, bear in mind, read this, you can just rewind this if you wanted to. If you want to listen 1,000 times, rewind this video. You need to make sure that if a smaller precedence like plus and subtraction, if smaller precedence comes to larger precedence, that larger precedence will be pop out and smaller precedence will come in, will be pushed. So it means, for example, plus is a smaller precedence, it's coming here, and multiplication is the larger precedence, so multiplication will pop out, addition will come in. So multiplication will be pop out and addition will come in. Okay, y will be print again multiplication, but the multiplication is greater than this, so multiplication, so nothing will change. Multiplication will come on top of the addition. It will only pop out once a lower precedence come to the higher precedence. Okay, now 3 comes, so 3 will be print, and we got the closing, so it's closed. Now whatever it is between these brackets, it will be pop out. So multiplication first and then addition. Okay, now we got division, and then we got 6. Wait, now we got divisions. So divisions will come, then we got 6 pop, will be print, and the remaining will be, and the remaining all if when we go through all of this, the remainings will be pop out, one after another. So right now it is only one, which is division, so division will pop out. So this is postfix. This is how you do in stack, and I've also done the programming for it as well. This is how you do it in stack, and this is the same exact answer which I have done it before. Same answer. I will show you how to do in graph, but for now let's see how to do in stack. So this is my programming which I have done in Java. But okay, we will yeah, this is the concept I have done in Java. Lower precedent, if lower precedent is less than the higher precedent, then it will pop out. I put a while loop in here, but we'll come to this, will come in P4. And okay, so this is the last one. Now let's do another example for stack. We got this example and we need to convert this infix to postfix. Okay, so let's start. So I have this stack, okay, and I'm going to print for new operands. Okay, so we got 8 will be printed. We got multiplication, it will come in here, open bracket, 5 will come in here, minus will come in here, 2 will come in here, closing bracket, which means anything between will be pop out, so minus will be pop out. Now we got another minus, okay, so minus is having the less than this, so multiplication will come in here, minus will come in here, 30 will be pop out, divisions is greater than this, so division will come on top. Then we got open bracket, then 2 comes in here, multiplication comes in here, 3 comes in here, closing comes in here, anything between will be pop out, so multiplication will be pop out, then division, and then subtraction. And I think it must be having the same answer, and I think yeah, it's the same answer. Okay, another thing I forgot to tell you, that if the precedent, for example, this is a stack, this is precedent 1, this is the precedent 2. If the precedent 1 is less than or equal to precedent 2, then precedent 2 will pop out. I forgot to tell you that it can also be equal to having the same precedent 1, precedent 2 having the same precedent, P2 precedent 2 will pop out. If precedent 1 is less than if the operator having less precedent than operator 2, then P2 again will pop out. Okay, if the operator 1 having greater precedent than operator 2, then nothing will happen. Okay, yeah, I assume. Okay, so we discussed about how to use stack. Now let's come to the graph, how to make binary tree. And binary tree means that having tree like this. Bi means 2, tree means tree, so having only 2 roots is known as binary tree. So this is a binary tree. Okay, or maybe we're not making a binary tree, we are making a syntax tree, I guess. Could be possible of having more than, I guess. No, I think not more than. It must be in binary. So how to make a binary or syntax tree, you can call it. We can use a syntax tree to convert an expression to RPN. To create a tree, the lowest precedent operator is positioned at the root. If there are several with the same position, the first one in order is used. So it is position at the root, which means the highest precedent will be at the top, but the lowest will be at the root. Okay, yeah. So for example, I got this a plus b, no, let me see how to create this. So I got the bracket, which means I'll start with plus, it contains a, it contains b, and then it gets multiplied by this, and again I got minus, so it contains c, it contains d, and there you go. We got the we got the syntax tree, and now we need to find the postfix. How to find the postfix? Okay, I got this trick right here. Supposing I need to find the postfix of this one. In order to find the postfix, let's suppose I'm finding the postfix of this tree. The trick is, first you go left, you go in order, left, right, and then print the root. Okay, first you go left, like I've gone left, then left, right, nothing there, root, which is 4. It comes back, it goes right, it goes right, left, right, root. Okay, 5 comes, it goes back, root, which is 2. Now it goes back, it is going right, it is going right, then left, right, root, which is 3. It comes back, and this is the root. So this is the precedence. So you are actually following the order. So it goes left, right, root, then comes back, right, right, root, then it gets a root, right, right, root, and then comes back and root. So this is how you can find the postfix of any syntax tree using this order. Okay, so the same thing here. I have created the tree. Where did I create the tree? There you go. I have created it, right? So left, right. Okay, left, right, root. This is A. Again, right, right, root, B. Left, right has done, plus remains, so plus. It comes back, right, right, root, C. Comes back, right, right, root, D. And then subtraction, which is root, and then multiplication. So I got the postfix, and it's the same thing. Okay, let's find the postfix for this one. First of all, I'm going to create the tree. So if I create the tree, let's say multiplication, I got x, then I got 2, and then I got plus, then I got multiplication, which is y and 3, and then addition, division, and then 6. So it's the same thing. Now I need to find the postfix of this one. Left, right, x. Right, left, right, root, 2. This one comes in. Then right, right, root, y. Comes here, right, right, root, 3. This comes then, and it will come then. Then right, right, root, 6, and then division. So you got the postfix for you, and the same answer. Okay, and it goes the same thing for this one as well. You just create this. For example, if I try to create this, let me just see. So I got the minus is connected to 5 and 2. Okay, then it is connected to, and I got another one which is multiplication having 2 and 3. Okay, I got these two. It is divided by something, so division and 30, and then again it is being subtracted. It has been subtracted, so this is negative, and I think it's going to be 2 multiplied by 3. Okay, division, then it's got 30, and then subtraction will come in between. Got this, and I only got this. Okay, so I'm going to, let me see. I have this side, I have this side. So what could be this? What could be? It might be the multiplication. Then I got 8, and I got this. Yeah, the same thing. Okay. And then if I want to find the postfix, then let's find the postfix then. So postfix, let's find it out. I got left, 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 right. This is the postfix. Then right, left, left, right. This is the postfix. 5 it comes in here. 2. Then I got subtraction. I got multiplication, and then I got here left, left. Okay, 30. It comes in here. Comes in here. 2. It comes in here. 3. It comes back, and comes back. And there you go. Look at the speed. Look at the speed, ladies and gentlemen. I just done it in few seconds. That's the power of this beautiful technique of mine. And congratulations, you have completed chapter 4 system software, and you have completed the translation software. And thank you so much for watching this video, and I'll see you guys in the next video. Thank you so much. Goodbye. I will see you in chapter 5. Goodbye.